These are examples from lesson 5.4, triangle perpendicular bisectors, medians, and altitudes. Example 1. In triangle XYZ, x is at 0, 2, y is at 6, 2, and z is at 3, negative 1. Find only the slopes of sides xz, right here, and yz, these two sides here. Then find the sides midpoints, these two. Then find the equations of each perpendicular bisector for those two sides, xz and yz. Use the two new equations to find C, the circumcenter of triangle XYZ. Afterwards, graph the triangle and check the location of the circumcenter. Now, the graph is already given to us of the triangle, but we are going to graph the midpoints and the two perpendicular bisectors. We only need 2 of the 3 to find the concurrent point circumcenter. Starting off, there are 4 steps. We're going to find the slopes first, then the midpoints, then we're going to find the perpendicular bisector slopes, then finally the equations of the perpendicular bisectors. Starting off with the slopes, these are the slopes of these two sides. The slopes of side xz and yz. First of all, the slope of xz. Remember, the slope formula is y2 minus y1 over x2 minus x1. So taking the ordered pairs, the endpoints for x and z, 0, 2, and 3, negative 1, I'm going to let z be my second point. So y2 is negative 1 minus y1, which is 2, back over to z, x2 is 3, minus x1, which is 0. Simplifying, we get negative 3 over 3, which gives us negative 1. That's our slope for side xz. Slope is negative 1, and it makes sense because it's falling. Then the slope of the other side, yz, this one right here, take the endpoints, y and z. I'm going to let z be my second point. Using the slope formula, I start with y2 first. Negative 1 minus 2 back over to point z, x2 is 3 minus 6. Simplifying, negative 1 minus 2 is negative 3. 3 minus 6 is negative 3. Negative divided by negative is positive. 3 divided by 3 is 1. So the slope of side yz is 1. Secondly, we're going to find the midpoints of those two same sides, xz and yz. Using the midpoint formula, starting with xz, the midpoint of xz is the ordered pair. This will be my first point, my second point, so x1 plus x2, 0 plus 3 over 2, comma, back over here, 2 plus negative 1 over 2. This gives us, simplifying, 0 plus 3 is 3 over 2, or 3 halves, comma, 2 plus negative 1, or 2 minus 1 is 1 half. So this is the midpoint of xz. Graphing that point, start at the origin, go 3 halves to the right. 1 half, 2 halves, 3 halves, up 1 half, 1 half. There's our midpoint. Midpoint at 3 halves, comma, 1 half. The other midpoint of yz, is using the same formula with these two endpoints. Z is my second point, y is my first point, so x1 plus x2, that would be 6 plus 3 over 2, comma, 2 plus negative 1 over 2. Simplifying, we get 6 plus 3 is 9 halves, comma, 2 plus negative 1, or 2 minus 1 is 1 half. So 9 halves, 1 half is the midpoint of side YZ. Graphing that, we start at the origin, go to the right 9 halves. 1 half, 2 halves, 3 halves, 4 halves, 5 halves, 6 halves, 7 halves, 8 halves, 9 halves, and then up 1 half. So this point right here is the midpoint of side YZ. It's at 9 halves, comma, 1 half. Next, now that we have the midpoints, these 2 points here and here are going to be the only point we have on each one of our new perpendicular bisectors. So we're going to find the perpendicular bisector of this side. We're going to use this point. We're going to find the perpendicular bisector of this side using this point. So step 3, we're going to find the perpendicular bisectors, both of their slopes. Well, the slope of XZ from the previous page was negative 1, and the slope of side YZ from the previous page was positive 1. Since the perpendicular bisector is perpendicular to those sides, or that side, the slope would be, we would use this formula. The slope of what we're looking for times the slope of the perpendicular equals negative 1. Or in other words, the negative reciprocal of the slope we're given. So taking the slope of XZ here, we want to find the perpendicular. So we use this formula. So the slope of XZ times the slope of the perpendicular to it equals negative 1, using that formula. The slope of XZ was negative 1, so we substitute that in, times the slope of the perpendicular we're looking for equals negative 1. Divide both sides by negative 1, and the slope of the perpendicular is negative 1 divided by negative 1 is positive 1. So the slope of our perpendicular bisector is going to be positive 1 for XZ. The other slope of YZ, we're going to find the perpendicular bisector. We need the slope, the perpendicular to it, so we use this formula again. The slope this time of YZ times the slope of the perpendicular that we're looking for equals negative 1. Substituting in the slope of YZ, which was 1, times the slope of the perpendicular we're looking for equals negative 1. Solving for the slope of the perpendicular, divide both sides by 1, and the slope of our new perpendicular is negative 1 divided by positive 1 is negative 1. So the slope we're looking for side YZ is going to be negative 1. Next, we find, step 4, the equations of the perpendicular bisectors. To do this, the first one we're going to find is the perpendicular bisector of XZ. We need the slope, and we need one point on the line. Well, this was the only point we have on our new line is right here because it goes to the midpoint of XZ. So this right here, 3 halves, 1 half is our point, and the slope we're going to use is right here. So the slope is 1, and the only point we have is 3 halves, 1 half. That's our X and Y coordinates. Using the point slope form of a line, y minus y1 equal m times x minus x1. We substitute in the slope, 1 here, and the x1 and y1 here and here. So we get y minus y1, which is 1 half, equals the slope, which is 1, times x minus x1, which is 3 halves. Simplifying this, use the distributive property here. 1 times both of these, it yields the same thing. So we have y minus 1/2 equals x minus 3/2. Then solving for y so we can get this into slope-intercept form, we add 1/2 to both sides. So this gives us y equal x, and then negative 3/2 plus 1/2 gives us negative 2/2. Simplifying further, we get y equal x minus 2 divided by 2 is 1. So this is the equation of the perpendicular bisector of side XZ. To graph it, we need the slope, again, is 1. And B, the y-intercept, is -1. Start at the origin, go to -1 on the y-axis. There's one of your points. Stay there and use slope, which is 1 over 1, rise over run. Go up 1 and to the right 1. We can continue that pattern and do more points. Take your straight edge, go clear across the graph, make sure it goes through the right points. And we get this line right here is the perpendicular bisector of side XZ. Then over here, for the other one, we're going to find the perpendicular bisector of the other side, YZ. Our slope for YZ was right up here, -1. And the only point we have on that line, that we'll have on that line right now, is this point here, the midpoint of side YZ, 9/2, 1/2. So this is our only point, so that's x1, y1, and here's our slope. Again, using point slope form, y minus y1 equal m times x minus x1. We substitute in the values. Y minus y1, which is 1/2, equals the slope, which this time is -1, times x minus x1, which is 9/2. Using the distributive property here, we get y minus 1/2 equals -1 times x is -x. -1 times -9/2 is plus 9/2, or positive 9/2. Placing this in slope-intercept form, we need to get rid of the minus 1/2, so we add 1/2 to both sides. We get y equal -x. 9/2 plus 1/2 is plus 10/2. Simplifying further, we get y equal -x plus 5 divided by 2 is 10 divided by 2 is 5. This is the equation of the perpendicular bisector of side YZ, right here. So to graph it, we need our slope. Slope was -1. And B, the y-intercept, is 5. Start at the origin, go up 5, positive 1, 2, 3, 4, 5. There's one of our points. Starting there, use the slope, -1. We could either use -1 over 1, or we can use 1 over -1. I'm going to use the first one. So I go down 1, and I go, that's my rise, and my run is +1. I can also go up 1 and to the left 1. Drawing my line with my straight edge, clear across the graph. Notice it goes to the midpoint, just like this one did over here. And this point where they both intersect is C, the circumcenter. The circumcenter is at 1, 2, 3 to the right, up 2. And there's our circumcenter. And these are the two lines of the perpendicular bisectors, the two equations for the lines. Example 2. In example 2, a town planner wants to locate a new fire station they want it to be equidistant from the elementary school, the middle school, and the high school. Here's the elementary, here's the high school, here's the middle school. They want it to be equidistant from all three of those schools. Where should he locate the station? To do this one, we need to find the circumcenter where all three of these points are the vertices of a triangle. So we want to make sure that it's located using this triangle right here. Somewhere in this vicinity. I brought the triangle out here so you can see it a little bit better. I also have already used my compass and straight edge and found the perpendicular bisector of 2 of the 3 sides. All we need are 2 of the 3 sides. It doesn't matter which 2. I used HM and EM. Notice on HM I used the compass to make these 2 arcs, and then I moved the point over here, made these 2 arcs. I used a straight edge and drew the perpendicular bisector of that side. Then I did the exact same thing, except I used these endpoints, E and M. Segment EM, used the compass on both ends of it, and drew my perpendicular bisector of that side. Notice where they both meet is right outside the segment HM, right outside the triangle. That makes sense because this triangle is slightly more than a right triangle, a little bit more than a right angle there. So it would be outside the triangle, but just a little bit. So if we estimate where that is, it's right about here in actuality. So this will be our new fire station right here. It's the same distance to the elementary as to the high school as to the middle school. So that is congruent to FS to E is congruent to H to FS and FS to M. The planner should locate the fire station at F. Take off the S there. The point of concurrency of the perpendicular bisectors. This point is called the circumcenter. Any 3 perpendicular bisectors, or 2 in this case, intersect concurrently at the circumcenter of triangle EMH and is what? Equidistant. It's equidistant to these 3 schools. Example 3. In example 3, in triangle ABC here, GE is 2x minus 7. So locate GE, 2x minus 7 from here to here. And GF is x plus 4. So GF right here is x plus 4. Okay. G, what is G called? It's called the incenter of the by the which theorem? Well, it's the incenter, G is, because the three angle bisectors are written here. Notice that C has an angle bisector and there's a segment going this way. A has an angle bisector going this way. They stop it right there. And B, angle B, or EBF has an angle bisector here. They all come together at a common concurrent point called the incenter. And so, according to your notes, by the concurrency of angle bisectors theorem, the distance between that point, the incenter, and all 3 sides, side CA, side AB, and side BC, are equidistant. So, from G to AB, it's the same distance. Remember, it's the perpendicular to the segment, as from G to side DA, perpendicular, point D, as is G to F, which is the perpendicular of CB. So since all three of these are equal in length, we can state that GE is equal to DG, which is equal to GF. Now the only two we need to solve this problem are GE and GF. So we're really not going to use this one. That's okay, because we can now just simply say GE equals GF. GE was 2x minus 7, that was what was given us, equals GF, which is x plus 4. Solving for x, we subtract x from both sides. We get x minus 7 equals 4. Then by adding 7 to both sides, we get x equal 11. So x is 11. We were asked to find GD. And GD, this side right here, since it's equal in length as the other two, we can choose either one of these expressions to find. So, since GE equals GD equals GF, I'll just take GF. GF was x plus 4. Since GF also equals DG, which we were asked for, we plug in the value for x, which is 11, plus 4, and we get 15. So even though GF is 15, so is DG, and so is GF. So DG is 15. Example 4. In the diagram at the right, XA, the length of XA is 8. So from here to here is 8. What is the length of segment XB? So XB is from here to here. So we've got XA, we're looking for XB. AB is a part of XB. Well, first of all, these are 3 special segments in the triangle. What kind of special segments are they? Notice that each segment starts at a vertex and ends opposite at the midpoint of the opposite side. There's 3 tick marks here and here. Here's another one. From Y to the midpoint, 1 tick mark here and here. And from vertex X over to opposite to YZ at point B, 2 tick marks here and here. So these are medians. And medians all come together at a point of concurrency. So by the concurrency of medians theorem, we learned that this whole, any one of these medians lengths, you take 2/3 of it and you get the longer piece of that median. So for instance, ZC is a median, and 2/3 of that distance is the longer of these 2 segments, which would be AZ. So the one we're interested in is XA. So we can say that XA, the longer part of this median, is equal to 2/3 times the entire length of the median, XB. And so we take what we know, we substitute it in. XA was 8 equals 2/3 times XB. And since we're looking for the length of XB, all we have to do is solve this equation. First thing we can do is multiply both sides by 3. The 3's divide out when we do that, and we get 24 equals 2 times XB. Then divide both sides by 2, and XB is equal to 12. So XB is 12 units long. Example 5. Two parts, A and B. Part A. In triangle PQS, PR is a medium, altitude, or neither. So we get a choice here. PR, locate PR. PR is right here. Notice that PR starts at a vertex, one of the vertices of the triangle, and it goes across or opposite to a line containing the opposite side, perpendicular to it. Okay, is that a median or an altitude? Medians, remember, as we just got through saying, go from vertex to the opposite side to its midpoint. There is no midpoint that this goes to. Plus, an altitude does go to the opposite side perpendicular. So this is the altitude. It's the altitude, or altitude PR. And then we can write since the segment runs from a vertex perpendicular to a line containing the opposite OPP side of the triangle. Part B. In the same triangle PQS, is QT a median, altitude, or neither? Explain. Locate QT. QT starts at a vertex, just like PR did, except instead of going to the opposite side or a line containing it perpendicular, it goes to the opposite side, to its opposite side's midpoint because of these two tick marks. What's that the definition of? Median. So, median, QT. It asks us to explain, so we explain basically by the definition of it. Since it, the median, runs from vertex Q to midpoint T of side PS in triangle PQS. One thing I want to point out is the explanation here was very general. It was just basically from the definition. The description here was the definition also, but it was in terms of this particular triangle and its median. Notice it refers to vertex Q instead of just a vertex. It talks about going to the midpoint T instead of just to the midpoint, and it goes to side PS instead of just the opposite side, and it refers to the triangle PQS.